As the disembodied voice said, I'm Dan Ridge. I'm a program manager in DARPA MTO. And as you heard from Whitney, MTO is an office that is full of fine, upstanding people who are experts in the design of microsystems, in the manufacturing of microsystems, the application of microsystems to hard defense problems. I, of course, am not one of those people. I am more of an expert in undesign and in unmanufacturing and in a variety of disciplines that today are swept up in sort of reverse engineering. And so given a device in front of me that somebody's already made, I'm interested in who made this device. When did they make this device? How did they make this device? Is it a copy of an earlier device? Is it a counterfeit device? How was it calibrated? How old is it? Where has it been? I think about things like that that are manifest in evidence from the manufacturing and design process. And so you might say, well, why do they let me hang out with them and eat their snacks? And the reason is exactly what Whitney said, that a lot at DARPA happens at the seams. And so I sit at the coal seam where we can do these things together and share. And so I will retreat to my notes. So the reason that they let me eat their snacks is that it turns out that the modern process of reverse engineering itself depends on a lot of manufacturing and design in order to get the artifacts you need to support that process. And so it turns out, though I don't think of myself that way, I find myself needing to design and manufacture hardware, and I support a portfolio of programs that do that. And we find that one of the things that we value most is speed. We need hardware not in 4 days or 4 weeks or 4 months, but sometimes 4 hours. And we find that when we're driven by a cycle like that, I can't anneal something for 12 hours if I need it in 4. I can't rinse it for 6 if I need it for 4. And that drives us towards non-traditional approaches. The need for speed drives, there's a hunger for locality that drives that and leads us to use unusual materials or repurposed materials. And in fact, one of the things we think about most with a system is, what else could it be made to do? Do I have a system that could contribute some hardware of its own to the diagnostic purpose? Can I make it do less? Can I repair it without additional hardware because I can't make it quickly? I think a perfect example of that that's very relevant to DARPA is the in situ annealing of the JunoCam. That's an example of a manufacturing adjacent process that needs the collaboration with the manufacturers. So I'm going to talk to you a little bit about novel hardware. And in fact, this is the slide in which I make a joke about the cutting edge. So one of the things we recognize at DARPA is no matter what we do, it's the warfighters at the edge who are the masters of innovation and improvisation. And so along that line, a story that I keep in my mind constantly is the story of the foxhole radio, invented on the beach in Anzio in 1944. So by World War II, it was relatively straightforward for our adversaries to identify a tube-based heterodyne receiver from emissions from the local oscillator, identify users of those radios and target them. And so it was imprudent at best for individual warfighters to be traipsing around with radios that could receive public broadcasts. And some of these broadcasts were in fact Axis propaganda broadcasts. Axis Sally was on the air covering the beaches at Anzio. Nonetheless, improvisation prevailed, and a recipe for an easily replicatable radio that could be made in a matter of minutes arrived. You use 1 part rusty razor blade, 1 part pencil lead, a few yards of wire wrapped around a cardboard toilet paper tube, and you have yourself a working crystal set. And so this is the kind of thing that we've been doing since 1944 that I'm trying to do in a more modern environment. Now, the thing about this is it sounds like a bunch of junk, but in fact it's not junk. These are in fact relatively high-tech materials. The supply chain it takes to manufacture, acquire in large quantities, ship halfway across the world, high-quality razor blades, copper wire, even toilet paper is really quite tremendous. So you have an asset there. You have a supply chain that can support anything that you can manufacture out of those relatively, for the era, high-precision parts. And so that's what makes them compelling. It's not a case that they banged rocks together on the beach and received AM. They took advantage of what the supply chain could deliver for them and made what they needed out of it. And so I don't want to leave you with the impression that if you have a rusty razor blade, you're not going to need a trillion transistor CPU. Now, I have colleagues here in the analog world who might tell you, in fact, that's fine. We can get you. And I think I have some colleagues in the quantum realm who might say, well, actually, it kind of depends on the temperature of the razor blade as to its practical utility for computing. So I don't want to tell you that a rusty razor blade is all you need, but sometimes it is. And so let me now tell you about this. So this is some data that's recent from the Federal Reserve, and it tells us what they, by their category, which is computer and electronic product value, what the value in unadjusted dollars is of computer and electronic manufacturing in the United States. There's a couple ways to think about this. One of them is we made about $32 billion worth of material in this category in the US last year. I want to put that in context for you in two different ways. The first is to say we made $75 billion worth of paper products in the United States last year. So not overall a really large number. It's also the same number that we made in about 1996. So a third thing I would say about it is, as you can see, we lose this capacity faster during periods of recession than we gain it back during periods of growth. So this is not a stable and a happy system. So I think if you think about dollars, it's hard to adjust the cost of compute for inflation because the technology is so intrinsically deflationary. If we think about this in terms of how many flops the American ecosystem is manufacturing, it's a staggering number and a huge success. If we compare it, however, to the insatiable demand for cycles, and compare it also to entire product categories that were made in the United States that have now been eclipsed, it's not as happy a story. So in 1996, at its peak year in revenue, when we were doing 32 billion electronics, Kodak alone was doing $17 billion in revenue. If you add Kodak and Xerox together, that's almost the entire value of computer output in the United States in 1996. So this is a little bit scary to me as somebody who wants to make sure that we can continue to manufacture things in the United States. And so I think there's a lot of deep investment that DARPA can make in this that we are making. And what I'm interested in is, what's our ability to leverage other things that we are good at? And how can we bring them back into the microsystem fold? And so I want to reconsider some materials that we have been considering for a long time, but for other reasons. We've been thinking about glass and paper and sugar-based solder masks and photoresists and other products for sort of a long time, but often based on the hypothesis that this will deliver lower cost or more performance or less toxicity or lower carbon emissions. And we often find that it takes a long time for those promises to come true because we're competing with a process shrink of the state of the art. And we find that double the productivity, you cut the carbon emissions. And so we don't find that we're able to move for any of these reasons. What I would say is, what do we do if the marginal analysis is not about the toxicity or the cost or the yield, but an existential one geared to making sure that we can continue to produce, even during times of conflict, the types of systems that we need? So I have three things here that I think that we're actually pretty good at making in the United States. Paper, we made $75 billion of it last year, and it is my top choice as an improvisational reverse engineer, whether I'm printing conductive inks, whether I'm manufacturing ad hoc connectors, whether I'm cutting starter stencils. No matter what it is, paper has, and paper's underused in modern microsystems. And I think it's worth an investigation about whether this is something that we have a supply chain that we cannot possibly lose. So I don't mean to be prescriptive about anything. This is really kind of an extended introduction for what I hope you will come talk to me about lunch and tell me I'm a complete idiot, or that you have an idea for how to use marmalade to get after some of these hard problems. Speaking of marmalade, well, we'll talk about that less. So glass is another technology that we're not going to be able to lose in the United States, and we have dumped a phenomenal amount of research at DARPA and in the industry into what its applications can be. Many of us use glass in our microsystems every day. What else can it do? The third thing I would say is, of course, sugar. That sugar has applications both as resist, as component, and the reason, actually, the impetus for this talk in my mind was this result by NIST from 2022 that was about sugar-based dye transfer to conformal surfaces. So that's a dye that they moved onto a human hair using sugar-based process developed in a beaker by accident, the way that all such things are developed. And so in addition to those types of materials that I would like to investigate further for their existential application, there are manufacturing facilities that we're at risk of losing. Some of them are facilities that have been producing goods for a long time and understand how to do them with mature supply chains. Some of the facilities are really quite new. In the last couple of years, I've toured a number of modern battery manufacturing facilities whose economic future is uncertain at the moment and whose pivot to microsystem support is not completely obvious. So rather than think about, does that make sense at all, think about that as a resource that could disappear and what can we do with it. And so that's really what I'd like to think about. But that sounds very gloomy, but actually I'm cheered because we have been here before. At the start of my career, obviously, the world of computing was informed by the Japanese fifth generation project that had started in the early 1980s. When we had, this is going to sound surprising to you, the United States had existential concern about our ability to be competitive in the computer field, and that an Indo-PACOM nation was going to get ahead of us in artificial intelligence. I don't know, has that ever happened to you? So what is encouraging about this story is that we were terrified. We made large national muscle movements as a result of this. We were terrified, but not paralyzed. And so it was this existential threat to our computing industry and our ability to do our strategic computing missions, whether they were for intelligence purposes, whether it was for stockpile stewardship, for our National Nuclear Security Agency, whatever it was for, we were about to lose our ability to manufacture. So consortium in Austin, supercomputing research centers, DARPA and others helped create IEEE supercomputing as a direct result of this existential threat. And what came out of it was not faster emitter-coupled logic or more aggressive liquid-cooled computers. What came out of it was a doubling down on the microprocessor as the unit of computing and a deep investment in how to parallelize a part that many supercomputers vendors at the time thought was complete junk, with interconnects that we thought were worse than useless. So within 5 years of recognizing that existential threat, the United States, every supercomputer vendor in the US at that time had pivoted to a massively parallel system based on a non-traditional HPC asset, the microprocessor. That was the Cray T3D, it was the connection machine CM5, it was the IBM RS6000 SP1. And so that may not seem completely non-traditional, like for like, silicon for silicon, but it really was a huge change and an embrace of what a lot of us regarded as a piece of junk lying on the floor. And so I think that that's something that we can bring in deeper and look to other parts of American industry that are stable to design systems. And also, finally, of course, I want to tell you about MacGyver, who was one of the real heroes of the mid-1980s. This was the best screenshot I could find to bracket our response to the Japanese fifth generation project, which is MacGyver in a kitchen, looking left at a Commodore 64 to see if that's the right answer to his problem, but also curious about that sugar on the kitchen counter to see if that was going to answer what the urgent need was. And that MacGyver remains an inspiration to us all, but I would say in the context of what we're talking about here, it was because he repurposed really high quality materials at the edge. It was not that he did it with rocks, he did it with high quality paper clips, and other devices. And so how can we be MacGyver in our manufacturing ecosystem? Thank you.